Laplace transform is a powerful tool for electronic circuit analysis, and to this lecture we will discuss about Laplace transform and its application to electronic circuits. So what is Laplace transform? Basically, it's a mathematical operator that operates on a time domain signal and converts it into a frequency domain signal. For example, we have a time domain signal f of t, and we define Laplace transform, which is denoted by this curly L. It's a mathematical operator. It will operate on this time domain signal and convert it into a frequency domain signal, f of s, where s is defined as sigma plus j omega. Usually in time domain signals or LTI systems, which is also known as linear time invariant systems, LTI systems, they are defined by a bunch of differential equations like this, or higher order forms, and Laplace transform will transform these differential equations into simpler algebraic equations into frequency domain, which is f of s. So it's much easier to deal with algebraic equations compared to differential equations, and we can solve the algebraic equations, find out the transfer functions from simple mathematical manipulations. But in time domain we have to use some complicated methods to solve the differential equations. So that's one of the greatest advantages to use Laplace transform in circuit analysis. So how do you define Laplace transform? That's the question. Let us say we have a time domain signal f of t, and the Laplace transform of this signal is defined as the integral of this time domain signal f of t multiplied by a complex exponential e to the power s of t dt, where s is sigma plus j omega. It's a complex variable. All right? So this is the definition of Laplace transform. One important thing to remember is that in order to have Laplace transform of any function, for example here in this case f of t, the entire integration should converge. If the integration does not converge, that means we do not have Laplace transform for this time domain signal. Alright, this is a very important point to remember. Let's take an example. Let's say f of t is defined as an exponential function e of a of t. This is an exponential decay multiplied by a unit step function e of t, which is defined as 1 for time greater than or equal to 0. That means positive time axis, the value of e of t is 1, and for the negative time axis it's 0. So this is like a straight line like this. Okay, this is a e of t function. When you multiply any signal, like here we have the complex, we have the exponential signal, and we multiplied it with e of t and our unit step, then the signal will be only it has value for the positive time axis. For example, the graph of the signal will be like this. Here it's the t, and here the axis is f of t. Since it's an exponential decay, it will start from the maximum point and start decaying gradually. And the function is only has some value for the positive time axis. It has no value for the negative time axis. So that's why we multiplied it with the unit step. Alright, we want to find out what's the Laplace transform for this exponential function. Then we take the Laplace transform and we just replace it with the integration 0 to infinity, and then f of t e to the power a of t multiplied by e of t, and then e of s of t d of t. A moment ago we just saw the value of unit step is 1 for any value t greater than 0. Since the limit starts from 0 to positive infinity, so the value of e of t should be 1. That means we just delete it, right? Just delete it. So we have just s of t and dt. So to find out the Laplace transform, we just need to solve this integration. And it's very straightforward. We simplify it in this manner. And then the integration is 1 over s plus a, s plus a. We have the limits value, 0 to infinity. And we can further simplify it, minus 1 over s of a. And then if you plug in the limit value, it becomes like this. Now, 1 over infinity is 0. What about this one? This is 1. So 1 over 1, just 1. And here we have a minus sign. So this minus sign and this minus sign becomes positive. So we have only 1 plus 1 over s plus a, which is the Laplace transform for this exponential function. In this way, you can find out any function's Laplace transform. You just need to solve this integration, and you can find out the Laplace transform for any time domain signal. All right. Now we will see the application of Laplace transform in electrical networks. And we will see how the life becomes very easy with the Laplace transform. Imagine we have an RLC network. Let's say we have a voltage source. This is the reference point, the ground point. This is RLC, and this is the input voltage V of IT. This is a very simple circuit, right? And the voltage across R is VR, voltage across L is VL, voltage across capacitor is V of C. All are function of time. Function of time. If you recall the definition of transfer function of any system, which is the ratio between the input and output and the input. So the transfer function of the system is defined as the output over input. Let's say we want to find out the transfer function of this electronic circuit, and the input signal is V of I, and we are taking the output across this cap. So V of C is our output. So the transfer function for this circuit will be simply V of C over V of I, right? We want to find out this quantity by using Laplace transform, all right? Now, before solving this electronic circuit, I'd like to write down a few theorems so that we can apply those theorems into the solution. The first theorem is, if we have a differential equation of this form, and if you take the Laplace transform of this differential equation, then we already know the Laplace transform actually converts the time domain signal into frequency domain. So in frequency domain, this differential, since this is a first order differential equation, so we just write down S, all right? And then for this f of t part, we write down f of s, and then minus of f of 0 minus. That is the initial condition. Initial condition is something, some conditions which are present before the analysis of the circuit. So we have some preserved value, for example, the charge across the capacitor, the magnetic field inside the inductor. But for the simplicity of the discussion, let's assume there is no initial condition in the system. So all initial conditions are 0 for this system. So for the sake of simplicity, we will just imagine this f of 0 naught is 0. So we can just delete it. So first order differential equation, if you take the Laplace transform, we can write down in S domain just the function itself multiplied by a single S variable. Alright? Now what happens if the differential equation is the second order, like this? And if we take the Laplace transform, then basically we have to write down the second order of this variable S. Since this is a second order equation, so we just take S squared multiplied by the function minus S multiplied by the function. Alright? Oh, sorry. Here, not the f of S, we just write down the initial values. F of minus of 1 minus f prime, the first differential of the function with the value of t equal to 0. So we already say that the initial conditions are 0. So we can delete these things. Simply delete it. Alright? So we will use these two theorems in our solution. Now, let's come back to the circuit. This is a simple RLC network. That means we can apply KVL, KCL, and Ohm's law in this electronic circuit to solve it. It has a single loop. That means we can use KVL, Kirchhoff voltage law, to find out the voltage or any or the current through these components. And to define, to use the KVL, we need to define a loop current I of t, which flows through all the elements of this loop. Now we are ready to define the KVL for this loop. So the voltage rise is equal to the voltage drop. This is the KVL, right? So V of IT, which is the source voltage, is equal to the voltage across the resistor plus voltage across the inductor and the voltage across the capacitor, according to the KVL. Now we can further simplify each component of this expression. So V of R becomes I times R, the Ohm's law, right? The voltage across the resistor is current multiplied by the resistance, Ohm's law. And we know the voltage across the inductor is defined as the inductance L multiplied by dI by dt. And the voltage across the capacitor is defined as 1 over C integration of the current. I'm using a dummy variable, tau, although tau is basically time, but I already used time in this equation. So in order to separate this to a variable, I'm just using tau for the sake of understanding. But basically tau is time, same thing. Alright? Okay, so this is the equation in terms of current. Now, remember, current is defined as the rate of change of the charge. I mean, I of t is defined as the rate of change of Q, which is the charge, right? We can simply include or plug in the value of I of t into this equation. So let's see what happens if we just plug in the values. V of it becomes V of it, it remains same. I of t becomes dqt by dt times R, and L dt dq over dt plus 1 over c 0 to tau I tau becomes dq tau over dt d tau. Alright? We can further simplify this equation. I'll write here. Vi t is equal to r dq dt r dq dt plus L. So there is a differential outside the bracket and there is another differential inside the bracket. So that makes second order differential equation. And then we have 1 over c, but we already have an integration and a differentiation, so they will cancel each other, leaving only q of t. Okay, so I revert back to the normal t variable because we no longer need tau. Okay. Now, remember, the transfer function for this circuit was defined as the output, which is v of c, over the input v of it, right? In this equation, we already have the input v of it, but we do not have the output quantity v of c. So we need to reformulate this equation in terms of input and output. How can we do that? Imagine we have a capacitor C and the voltage across the capacitor is v of c and the current is I of t. And the charge of this capacitor is Q, which is also functional time, d. Now the fundamental relationship between the charge and voltage of this capacitor is defined as Q of t is equal to C, the capacitance, multiplied by the voltage across the capacitance, which is V of Ct. Alright? We have Q in this equation, so we can just simply plug in the value of Q and reformulate this equation in terms of the voltage across the capacitor. So let's do that. V of it R, and this C becomes here, and then we have the differentiation of the voltage across the capacitor, and then inductance L multiplied by C d squared V of Ct plus T squared. Now, Q of t means C multiplied by Vc, right? So this C and this C will cancel each other, leaving only V of C, leaving only V of C. Alright, so we now have an equation that involves both input and the output quantities. So we can now derive the transfer function from this equation. We can solve this differential equation and take the ratio of V of C and V of I in time domain. Or we can apply Laplace transform and formulate a simple algebraic equation which can be very easy to deal with and find out the ratio between the input and output quantity to find out the transfer function. So let's take the Laplace transform in both sides of this equation. L, the curly L denotes the Laplace transform. So I just took the Laplace transform in both sides. So it becomes V of I in terms of S variable, the complex variable in Laplace domain. So each time domain quantity will be converted into an equivalent S domain quantity. Alright? And R, C, they are actually constants, so the Laplace operator will not work on these constant quantities. And this, remember the first theorem, if we take the Laplace transform of a differential equation of first order, we get an S variable multiplied by the function. So we will apply the same theory here. We have a differential equation here, and if we take the Laplace transform, then it becomes S multiplied by the function in S domain. All right? Now, for the second part, LC, they are constant, so they will remain the same. And this is a second order differential equation. That means we will apply this theorem. So it will be S squared VCS plus. It's just simple VC, so we will just write a simple VC S. Very nice. So the differential equation has been converted into simple algebraic equation in terms of variable S. Now it's very easy to deal with. V of IS, take VC common because it's common in all terms. RC and S squared LC plus of 1. Now, to find out the transfer function, we just need to take the ratio between V of C and V of I. So you can take the ratio V of CS, V of IS, which is 1 over S squared LC. I'm just rearranging this equation, SRC plus 1. So this is the transfer function of this RLC circuit by using Laplace transform. See, I did not need to solve this differential equation, which is a lengthy process. And after solving them, you have to take the ratio in time domain V of I and V of C. That's another story. It's a long process. By simply applying the Laplace transform, we just took the ratio and we found out the transfer function. And we can simply represent this entire circuit in a square block like this, having a transfer function of this much, S squared LC plus SRC plus 1, where we give the input as V of I, S, and get the output across the cap V of C of S. So this is the block diagram of this RLC network having a transfer function of like this. This is a very handy representation in terms of system analysis. So Laplace transform is really super for analysis of these complicated electrical networks. Let's see another example. Let's say we have an op-amp circuit. This is R1, C1. This is input V of I, T. And we have the output V of OT, having a negative feedback load, which consists of R2 and C2. So this is a non-inverting amplifier, op-amp amplifier. So we have the input V of IT and the output is V of OT. And we have a feedback loop here, having a resistor R2 and C2. Now if you recall the theory of op-amp, we know the transfer function of op-amp is defined as the output over the input, which is negative of Z2 over Z1. Now Z2 and Z1, they are actually impedances of what? Z2 represents the impedance at the output load, feedback load, Z2, and Z1 represents the impedance at the input side. So if we take the ratio between these two impedances, then we can find the transfer function of this open circuit. Alright? We do not need to go through the stages of writing differential equation and solving them. We can skip those parts. So the concept is impedance transformation. Impedance transformation in Laplace domain. Alright. Now before solving for the transfer function of the circuit, I would like to highlight the impedance transformation in S domain or Laplace domain. Imagine we have a resistor R having a voltage V of R. Let's say it's a capital V because we are dealing in S domain. So the current is I of S. Now what is impedance? Impedance is a ratio. It's a ratio between the voltage and the current inside the circuit, right? The ratio of these two quantities will give you the impedance across the terminal. Now, VR over IS is what? The impedance of the resistor, which is simply R. So resistor is very simple quantity. Now let's talk about the capacitor. The value of capacitor is C, having a voltage V of C, which is a function of S variable, and obviously we have a current I of S. The impedance of capacitor will also be the ratio between voltage and current, right? Now, from the theory of basic capacitor circuit, we know that voltage across the capacitor. Let me write it in time domain so that you can understand, you can follow me. The voltage across the capacitor, or better if I start from the beginning, we know the current across the capacitor is I of C, C dVc by dt, right? Okay. Now if we take dt in this side, what happens? C dVc I of ct dt, right? And if we take the c in this side, then 1 over c, and then take the integration, right? Then this quantity becomes the voltage. So in time domain, the voltage across capacitor is 1 over c, and integration of the current from 0 to t, at a certain time period, t, all right? Now, in the previous example, we saw any time domain function like having a single, first order differential equation can be converted into Laplace domain by simply writing a variable s multiplied by the function's S domain equivalence. What about the integration? Say we have a function and we need to integrate it and then take the Laplace transform. So what is the equivalent Laplace transform quantity of an integration here? It's very simple, just think about it. It's the inverse. The differentiation and the integration is an inverse process. So that means we have to take 1 over s. So any integration in time domain will be translated into 1 over s multiplied by the function itself f of s. So if we apply here, then we get v of c of s 1 over c, and that is what? That is 1 over s multiplied by I of s, right? And then we can get the ratio between the voltage and current. Just bring the I of s over v of c, then we can get the impedance of capacitor as 1 over s of c. So this is the impedance transformation in S domain of a capacitor. Alright, so I'll write it clearly here for your reference. So for resistance, we had, it's a simple R in S domain. For cap, the impedance was S of C. Alright? Now let's talk about the inductor. What would be the impedance of inductor in S domain? Imagine we have an inductor L having a voltage across it V of L and a current I of L, or just I. Let's say they are in time domain. And from basic inductor circuits, we know that V of L in time domain is defined by the inductance multiplied by the differentiation of the current. Now, applying Laplace transform on both sides, what happens? V of L, S, L is a constant, so we can take it out, and this becomes S multiplied by S. So if we bring IS here, so we have simply S of L, right? So this is the impedance, the equivalent impedance in S domain of inductor. So we can write it like this. The impedance is S of L. So we will use this formula when solving this circuit, op-amp circuits, to find out the impedance Z1 and Z2. Okay, back to op-amp. So we just saw the transfer function of the op-amp circuit is the ratio between Z2 and Z1. That means we just need to find out the Z2 value and Z1 value. Alright? Now, let's consider Z1. Z1 is a parallel RC network. That means R1 and RC and C1, they are in parallel. Now, if you remember, if we have multiple parallel resistor or whatever the component, let's say a resistor, then the equivalent parallel resistance is 1 over Rp is 1 over R1, 1 over R2, 1 over R3, and dot 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 dot. Alright? So since we have R1 and SC1 in parallel, we can follow it up like 1 over Z1, which is the equivalent impedance of this parallel network, is equal to 1 over R1, the impedance in S domain, plus 1 over, what is the impedance of C1 in S domain? SC, right? So instead of SC, it should be SC1. In this way, 1 over SC1. Okay. Alright. So it becomes what? 1 over R1 plus SC1. Since this is Z1, so we can further simplify it like R1, 1 plus R1, C1, S. Yes, it's 1 over Z1. And if we just invert it, because we have the reciprocal, then Z1 value becomes R1 by 1 over S R1 C1. So we got C1. Now time to find out the Z2. Once we find out the Z2, then we just take the ratio and put a minus sign in front, and then we can find out the transfer function. It's very straightforward. Even in Z2, I mean the output feedback loop, it has a series element, so you just add them up. Just add them up, like Z2 is equal to the impedance of the R2 in S domain is R2. The impedance of C2 in S domain is simply SC2. Just add them together. Alright? And then you get what? You can simplify or you can just write it directly. It's up to you. The transfer function becomes negative of Z2 R2 plus 1 over SC2 divided by R1 divided by SR1 C1. Okay? Great. So, This is the transfer function for this open circuit. See, I didn't write any single differential equation to solve this open circuit to find out the transfer function. I just applied the impedance transformation concept in S domain and then took the ratio between them and find out the transfer function without going through the long stages of writing the differential equations or even KVL, KCL or Ohm's law. I just wrote it, I just applied the impedance transformation. So Laplace transform is a powerful mathematical tool that provides a lot of freedom, a lot of room to solve the circuit from different points of view without applying any complicated differential equations. Usually for the time domain differential equations, they are very difficult to solve, and some differential equations, even the solution does not exist for them. We have the existence and uniqueness theorem of differential equations for the solution. And in S domain, all the expressions you can see, they're just algebraic. It's very easy to manipulate them, to solve them, to find out any variable here, right? But for differential equations, the solution is not straightforward. So that's the beauty of Laplace transform. And all the engineering disciplines, they use this Laplace transform in order to solve their own version of the problem. Electronic engineers, they do use it a lot, and that makes our lives very easy. I hope I clarified the concept, the basic concept of Laplace transform and its application to electronic circuit analysis. Thank you very much for watching my lecture.